I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast to help you understand the chemistry of your everyday life.
Yay, I'm so excited. I am recovering from a cold a little bit, so if I sound a little nasally, that's why, just for the record.
Not your fault. You're forgiven.
And if I'm a little sniffly. Okay, so I'm really excited for this episode. I guess I always am excited for the episodes, but we got this question from SD Pete on Instagram.
Okay.
And it's really such a good question. And then after they asked it, I was laying in bed and noticed a light blinking in my bedroom. And I was like, is that our smoke detector? And then it was really in my mind.
Ah.
So SD Pete asked how smoke detectors work.
Okay.
And I think I want to expand this into a multi-part series because there's two different types of smoke detectors and there's also those sprinklers.
Oh, right.
You know, that go off.
Yeah.
And guess what? They all work by chemistry.
Oh, interesting. Are you sure?
I'm positive.
Okay.
They all work by chemistry.
All right.
Okay, so there's two kinds of smoke detectors. So let's talk about that.
Okay.
We're going to talk about one today and leave the next one for the next part. So the one we're going to leave, it basically uses a light to sense particles. Fairly straightforward. We can talk about it in the next episode.
Okay.
The other kind is called an ionizing smoke detector. So it's a little bit more complicated, and that's where we're going to zoom in today.
And is the ionizing one more of what most of us have in our homes, or does it really vary a lot?
I don't know which one there's more of, but I do know that I had to use a lot of government resources for this. There wasn't a lot of just chemistry resources on how smoke detectors work.
Uh-huh.
But one of the government websites that I used recommended having both kinds because they're good for different types of fires. And there are some that incorporate both like in their little in one.
Okay. Yeah.
So like they have it's like a dual sensor or something that's both technologies are used in there. So maybe that's the most common, but they do recommend using both kinds.
Okay.
And it did make me wonder what I have in my apartment because it's not a house, so I didn't buy them.
Right.
Do you know what you have in your house?
It's funny that you asked this because literally, I don't know what kind.
I could tell you were dying to say something.
Well, it's just funny. This has happened sometimes where like the topic that we pick, not every time, topic we pick has something like related to something recent in my life. It was maybe about 2 weeks ago. I was cooking and I started thinking, where's the nearest smoke detector in here? I looked around in my kitchen and there wasn't one. I thought that's not great, but you know what?
That's a little weird.
That's weird. But you know what? In other houses would have had one right near my kitchen. Sometimes it's actually been too sensitive.
That's what happens in ours. It goes off all the time.
Yeah, just a little bit of smoke. So I was like, maybe it's better. And so I thought, oh, you know what? Maybe I think it's right over our dining table, somewhere around there. Mm-hmm. And I stepped back and looked, and there wasn't one there.
Oh no!
And then I looked like, okay, well, we have a fireplace in the living room. Maybe I'll go step a few steps further back. Maybe I have one in my living room. There's not one in my living room.
Oh no! In that whole area?
In the whole area where the fireplace and the stove and the oven are, there's not one.
How is that up to code? Isn't someone checking something?
I mean, it's probably not. And that's the weird thing about, especially in states like Texas, where older homes get sort of grandfathered in on some stuff. I mean, I'm sure everyone inspector probably did maybe tell us something like that. And I'm sure that there is a code to it, but I'm not sure if they can force you or whatever. But if you're building a new house, they can force you where to put them. The nearest smoke detector in our house is all the way down our hall, right near our bedrooms, which obviously
that's good if you're sleeping.
Yeah, good place for them, but not a good place for your main one.
Right.
And the smoke's gonna get way down there, right by our doors.
And then
we'll be made aware of it.
It'd be better if we were made aware of it sooner.
Yes. So I'm interested in this topic.
Okay.
And I'm interested because I will probably soon be in the market
right.
for some new smoke detectors.
You probably should purchase some. Yeah, I think so. Okay, so we're going to talk about the ionizing smoke detector, but now I want you to just like pause that, hang it up on a hook.
Okay.
And think instead about radioactivity. And there's a reason we'll come back to.
Radioactivity. Okay.
Yeah. So what do you know about radioactivity?
What I know is from the show Chernobyl.
Oh, I didn't watch that show.
Oh,
I thought it was going to make me too sad.
It's really good. It is sad though, but it's really good. Okay. I feel like my understanding is that there's a lot of instability with some element. I feel like I've heard the term like uranium and a few other like, isn't it like specific isotopes of atoms that they use of a substance that makes it good for those conditions?
There's certain ones that are naturally radioactive.
Okay.
Yeah.
Okay. And that there are like particles like flying in different directions and stuff like that. Like,
okay. Yeah, that's true.
There's a sentence in that show where the guy basically says there are atoms of this element, like basically firing all directions like bullets, making tiny holes in everything in this radius. And it's like he's trying to convince him it's a serious deal. And it works for me. It worked for me. I was very convinced that it was serious. But that's kind of it. I just know that's bad. I know you can measure it with the Geiger counter stuff or whatever.
That's actually not a bad starting point.
Okay.
I think the idea of things flying around, like sort of all atoms all the time are shooting around in all directions.
Right.
So
right.
that I'm like, but
right.
And I don't know what context he was talking about it in, but it's the instability and things kind of shooting out is not a terrible mental picture to have.
Okay.
So when I talk about radioactivity in chemistry, I think about an atom that's unstable, like you said, and it usually is breaking down or releasing energy in some way to become more stable. Okay. And it actually goes really well with last week's episode. You know, we reviewed, or 2 weeks ago, I guess, we reviewed the different parts of the atom, how there's a center of the atom that has protons and neutrons, and then there's the electrons on the outside. So that comes into play because when atoms break down, they are in radioactive decay. Oftentimes they're literally losing parts of themselves. And sometimes their identities change. If they lose those protons, their identities can change.
Right, right.
So that's kind of a big deal.
Yeah.
Okay, so that's in radioactive decay. The way I phrased it here is they essentially lose parts of themselves and they can change identity. And it just as kind of a broad overview, they can lose energy, neutrons, protons, electrons, and they sometimes as a result become a different atom. Okay. So they can lose anything. They can give off anything kind of.
Dang, wow.
I know. And there's lots of different types of radioactivity or radioactive decay, but they're typically becoming a more stable atom with each breaking down or emission of energy.
Okay, that makes sense. They want to be stable if they can.
Yeah. Okay. They're trying, it's sort of like a desperate attempt to be stable. And there are some...
I mean, I identify with that so much.
And there are some elements that like they start out really unstable and they'll break down into something else that's more stable, and then it breaks down further, you know? So one of the things we're talking about today is actually a byproduct of another thing breaking down. Okay. So, and it will break down into something else that's also radioactive, you know? So it can keep breaking down. Okay. So there's different kinds of radiation, different things that are emitted, but today I want us to focus on two things which relate to today's topic. So those are alpha emissions and gamma emissions. Okay. Did you hear about either of those in the Chernobyl?
I think I heard about gamma in Chernobyl.
That's the most common one.
And gamma also finds its way in pop culture in other ways, like, you know, Bruce Banner, Hulk. Gamma radiation is how his whole origin story comes about.
Oh, I did not know that.
Yeah. So I bet a lot of our listeners, that might be one of the ways they've heard of gamma is like superhero stuff. It's like the way of like grabbing some words from science and throwing them into a superhero origin story. That one, I guess, has been used.
You know, that doesn't bother me a ton when it's like, oh, this is so unrelated to science. They just took these fun words. But you know what really bothers me is when they're pretending to be scientific and then they do something like touch their cell phone with their gloves. It's like a deep-seated, like, oh, don't touch that with your gloves.
Yeah.
So that kind of like, oh, you're just making this science fiction. You're acknowledging that it's fiction. That's fine. Yeah. But when they're doing scientific things and they touch their phone with their gloves, I'm like, I don't know if I can watch this.
Yeah.
Okay. So alpha decay, we'll talk about that first, is what happens when an atom loses so-called alpha particles. Okay. So alpha particles have 2 protons and 2 neutrons. Do you know what else has 2 protons on the periodic table?
Oxygen?
No.
Dang it.
I mean, it has 2 plus 4 more, I think. 6.
Oh, man. Okay, wait. Hydrogen is 1.
Uh-huh.
And then, well, I kind of think it was next. Is it helium?
Yeah, it's helium.
Nice.
So, yes, helium has 2. And so essentially what alpha particles actually are is they're the same size as a helium atom that's lost its electrons. They are helium 2 plus, basically.
Okay.
Because if you lose your electrons, you're positive.
Right.
I've told that joke that my cousin told me a lot, where the atom runs into a bar and says, I think I lost my electrons. And the bartender says, are you positive? Right. So it's essentially a positive 2 plus or positive helium atom.
Okay.
But so it's like kind of big compared to some other types of radiation because it's essentially the same size as an atom.
Okay.
And so because of that, kind of moves slow, and it's not really as dangerous is my understanding, because it's big, moves slow, can be easily stopped.
Okay.
Other types of radiation are harder to stop.
Okay.
Okay, and then there's also gamma particles, which are not gamma particles, I guess. I should walk that back. There's also gamma radiation.
Okay.
And gamma radiation is actually similar to what we've talked about before when we've talked about excited electrons and how then the electrons will move back down and sort of shift from a higher excited energy state to a lower energy state.
Right.
And when they do that, they let off energy.
Yes.
So gamma energy is basically that, where an excited electron relaxes back down to the ground state, but it just so happens that the exact amount of energy between the excited and the relaxed states is in the gamma range on the electromagnetic spectrum. So it's just, they just essentially give off radioactive energy instead of visible light or something like that.
Okay.
Yes.
I see what you're saying. Right. Yeah,
So
because we've talked about that where we can see it visually because it's in the range of visible light.
Yes.
And there, in this situation, it is in the range of gamma radiation, not in the range of visible light.
Yes. So there's that electromagnetic spectrum, which I feel like is often, it's got the rainbow in it. And then sometimes it uses other colors to represent like infrared, microwave, whatever. And so it just so happens that these they don't give off microwaves, they don't give off visible light, they give off gamma radiation as the exact space between those electrons that's giving off energy.
Is that higher than or lower than the range?
I can never remember. I always have to go look up because it's like wavelength and frequency are opposite.
Right. I wonder if, because infrared's lower, ultraviolet's higher. Right? Yeah.
I can pull up the electromagnetic spectrum real quick and we can look. Okay, here we go. The electromagnetic spectrum. So radio waves and microwaves are on the far side of the visible region.
Okay.
With infrared. And then on this side, on the nearer side, is ultraviolet, X-ray, and gamma ray.
Got it. So as it's starting to get more faster,
higher energy, smaller frequency, smaller wavelength.
Yeah.
I always get those because they're inverted. I always have to look those up.
Yeah.
But yeah, so there's higher energy. So essentially, they're just shooting out dangerous energy when they relax.
Okay. Got it.
So
dangerous energy,
not just visible energy. I mean, even the ultraviolet is dangerous.
Right.
X-ray is dangerous, and then gamma is even more dangerous.
Okay.
Is a kind of maybe a good way to think of it.
Okay.
Maybe then I want to look it up every time if I could just remember that. Because ultraviolet, that's what damages our skin. We've done a lot of episodes about that.
Yeah, 100%.
And we also can't see that, which is fun to imagine being able to see it.
Yeah.
Okay, let me find my place here. Okay, so we've gone over the two sort of types of radiation that are going to come into play. And I don't know if I hit this hard enough, but with alpha radiation, with the alpha particles and the alpha decay, when you're losing those 2 protons, the original atom that's giving off those 2 protons and 2 neutrons, it's changing identity. So it's breaking down into something else.
Right.
So in the case of smoke detectors, which are probably like, what does this have to do with smoke detectors?
Yeah. It's like, are they detecting radiation in
No.
our homes? Hopefully not.
They're generating radiation.
Oh.
I know.
Okay.
But it's safe.
Okay.
Okay, so in the case of smoke detectors, safely protected inside your smoke detector, there is a little bit of radiation happening.
Okay.
So it's small, it's a protected space. I sort of got conflicting information and I couldn't find a good scientific paper on this.
Mm-hmm.
Some said that there's gamma and alpha particles. The other said only alpha particles. I keep saying gamma particles, but I guess I just mean gamma energy.
Okay.
So gamma decay and alpha decay, I've heard both of those. And I also heard just alpha.
Okay.
To me, just alpha or primarily alpha radiation makes the most sense because it'd be really easy to stop that from leaking out.
Right.
But it also is a very small amount. So maybe because it's so small, it's not really dangerous to have that in our smoke detectors.
Okay.
But it is safe.
Okay.
So in our enclosed space of our smoke detectors, there is usually like some kind of metal. And in the very center of the metal is a little bit, like 100 nanograms or less of something called americium. I never know how to say those.
Okay.
It's an element, and it's a radioactive isotope of the element.
Okay.
And there's just that little bit of it. And in addition to that, there's a positively charged plate and a negatively charged plate. So like an anode and a cathode, if you want to use the fancy words for it.
Okay.
So what happens is the americium emits alpha, possibly also gamma particles. And when those are emitted and they interact with the air, it will ionize the air, the molecules in the air.
Okay.
So it kind of bothers me when people are like, oh, it ionizes the air because the air is nothing, you know?
Right. Like what elements, what atoms is it?
Yes.
Yeah.
So the atoms that are in the air become ionized, which sort of the way I picture it in my mind is like, oh, we're shooting out these positively charged heliums, basically, and they come into contact with something else and they can take the electrons from that thing. And then now that thing is positively charged and it's going to try to go, get something. And so now we have all kinds of different electrons being shifted around back and forth, making some positive ions in the gaseous molecules in the air and some negative ions.
Okay.
And then you put that between two positively and negatively charged plates, and they'll kind of nicely organize themselves and create a current running between those two positively charged plates. And this reminded me so much of when we did the batteries. It's like the ionized electrons bridge the gap there, and they make a current. They close that, the gap between those two positively and negatively charged plates. They complete the circuit, so a current is running through at all times your smoke detector.
Right. Okay.
Now, when smoke particles start to move through the air and get into our smoke detector, they'll start to interact with those ions and disrupt those ions.
Okay.
And I'm assuming other things might also, but if it's low enough concentration, I feel like probably your smoke detector is fine, just sort of, mitigating that. It's like, one or two, not a big deal. But if enough particles start to float in and it disrupts the flow and the current, the flow of electrons and the current in the smoke detector enough, the smoke detector recognizes that the current is shut off, sort of like if you took the batteries out of something and it's not working anymore.
Okay.
And that sets off the alarm.
Okay.
I sort of thought of it like the Indiana Jones, like once that weight is taken off, the alarm is sound, the booby trap is triggered.
Yes.
So I feel like it's similar. Once the current is gone, once the batteries are taken out, essentially, the batteries that the americium makes, it sends off a danger, kind of thing.
Okay. Interesting.
So that's how the ionizing smoke detectors work.
Wow.
So a little bit of radiation chemistry, that's your chemistry lesson, and then put it into the context of the smoke detector.
Okay. Wow.
So we haven't had like a brand new chemistry information lesson in a while.
Yeah. That's definitely a lot there, and certainly way more than I would have expected.
I know.
Smoke detectors.
What do you think you thought happened in them?
I guess I thought there was some specific element that maybe it could like kind of detect for in smoke, that like maybe isn't already in the air. but that might not really be true. Or like, how would it detect it? I mean, how, other than something like this where it interrupts the circuit,
Well, I can think of one other way, but I won't tell you till next week.
Okay. Right. But I mean, like, that's just one of those things where like that answer served me fine for a while. Like, oh, there must be something in smoke that it can tell. But clearly, I couldn't really bridge the gap very much. That's so crazy.
I know there's literally a little bit of radiation. Also, radiation just by itself to me is crazy. I mean, because I guess I didn't say this, but I probably should have. The Americium, it looks like America, so that's why I don't know how to say it really.
Yeah.
Americium emits these alpha particles, and it actually breaks down into neptunium.
Okay.
Because it is getting rid of its protons.
Right.
So it changes identities right there in your smoke detector.
And so is that probably one reason why smoke detectors only last so long? Like they have a shelf life.
I would think so, actually, yeah.
There's a finite number of these atoms here that are doing this thing.
That's my guess.
Okay, interesting.
I don't know for sure, but I did think about that while I didn't realize that smoke detectors had a lifespan. But while I was doing this, I was like, well, what happens when all the americium is broken down to neptunium?
Yeah. That's crazy. Yeah, I guess that's why. Or like, I mean, maybe they also just get less effective and maybe it require too much smoke to like really be safe at a certain point.
Yeah, maybe so.
Where it need to, I don't know. That's crazy. I have like kind of two analogies floating around in my head.
Okay.
That, could either of them work. We'll just see what happens. Okay. So
lay them on me.
The first one is probably similar to what, I don't remember exactly what analogy we ended up using when we talked about batteries a while ago. But, there's just there's a flow of something like say traffic, and if something interrupts that, then it's messes everything up. If it halts the flow, then that's something that we've all experienced the downside of. And so it's not that hard to imagine that happening in like this very like electron subatomic, whatever way, where there's a flow that's happening and if something interrupts it, it's detectable.
Yeah.
And you could have something set it off. So if those smoke particles that are starting to float up and get in with the air, the atoms that they're helium. Wait, sorry. Let me start over. The atoms of the
Americium. Yeah, I think. I always say it wrong. Americium.
They are positively charged. And they would rather be stable, correct? They'd rather have electrons to make them even. And so as they are being
2+, that's crazy. For such a tiny little, it'd be like basically a hydrogen that has 2 positive charges. That's a lot for a little atom like helium.
So as they are able to steal electrons from the atoms in the air, they are happy if things are going well and stuff. But if smoke starts getting intermixed into that, they can't do that. And that's a piece I'm missing. Dang it.
So you miss the charged plates.
Okay. Yes. Charged plates.
They line up. So I think it ionizes the air. It goes and interacts with things. There's lots of reactions happening to ionizing molecules in the air. Right. And I think probably the energy that's emitted, if there is the gamma energy, which was not clear to me, I got conflicting information. That probably also putting energy into things helps them react or helps them move around and interact with other things. Okay. So there are positively charged and negatively charged things now floating around in this little contained space of your smoke detector. Right. And then the charged plates line them up.
Yes. And the charged plates line up and things are flowing correctly and everything's happy until smoke starts getting in there and messing up with that flow and this little self-contained kind of ecosystem almost.
Yes.
Of charged things getting what they want and exchanging, electrons and flowing and all that kind of stuff that interrupts that. And something in the smoke detector, just like say, I don't know, a traffic reporter or whatever, is going to be looking for that all the time. And as soon as it happens, it's like, red alert, there's traffic here.
Yeah.
Something is not working as it should. Our little happy ecosystem community is being altered in some way.
Mm-hmm.
So that's one thing I thought of, the traffic deal.
Yeah.
But another thing I kind of was in my head was just like, you know how in movies when
Oh, God.
someone is,
I feel like this is going to be dumb.
it's not quite as dumb as it seems right now. Whenever someone has really, actually this is true. Well, yeah, this is true in Chernobyl, not to the degree I was thinking, but when someone has really good, really important information that people don't want to get out,
Ooh,
you know,
yeah.
there's that moment where it's like
in Aaron Brockovich.
I haven't seen that. That's like the second time in the past 2 weeks someone's referenced that, and I have
It's
no
good.
idea what any of that is about.
Okay, sorry.
Other than Julia Roberts is in it.
Yeah, well, it's also chemistry, but it doesn't matter.
Okay. Anyway, I need to watch that movie, I guess, and read her Wikipedia page. So whenever someone has important information that other people don't want out, you know, you have a meeting and you say, like, if I don't call so-and-so, if I don't call my contact after this meeting at midnight, they're going to send out this package to the New York Times or whatever. There's a standing order
Yes.
to follow this thing and send this thing out
Yes.
if I don't stop you or whatever.
Yes.
So I kind of think like you could sort of reverse engineer that into the smoke detector.
Like, we'll sound the alarm if we don't hear from you.
Yeah.
Mm-hmm.
If for any reason our flow of communication stops, sound the alarm.
A lot of times women do that on dates.
Ah.
It's like if you're going on a date with someone you don't really know. I mean, men should probably do this too, but I think women are maybe a little bit more vulnerable because we're oftentimes smaller than the person we're meeting.
Yeah.
It'll be like, okay, if I don't hear from you, I'm gonna start to get worried. So like turn your location on so that I can sound the alarm. So it's kind of it is kind of like that.
Text,
like
check in. If you don't check in by 10, then yeah.
When the flow of information is interrupted, then we start to get worried.
Yeah.
And that is like when the flow and the current is interrupted,
Yeah.
then the alarm goes off.
Send out the classified documents. Do
Yep.
it. I didn't tell you to stop. Do it. And then that's when the smoke detector goes off.
Yeah.
Something like that. So a mixture of traffic and spy movies and dates with strangers.
Yes. So when I'm not getting the information that I know everything is okay, the smoke detector, it's like 1 or 2 interactions, not a big deal. But if there's an interruption, smoke detector freaks out.
Yeah.
It's like if it takes you longer to text back, okay. But if I don't hear from you for 10 minutes, I'm like, she's dead. I don't know.
Yeah.
So that's a good analogy. I like that.
There's definitely enough there where I'm like, this is a tough one, but I think I get the gist of it. But there's so many little parts of it that I feel like it's just, I don't know. It's hard.
Yeah.
It's harder than I expected it to be.
It's like step 1, you get radiation emitted. And then step 2, that radiation, depending on the type, at least the alpha, we know, particles, and then possibly gamma energy facilitate some of this, causes the molecules in the air to be ionized. And then step 3, they all line up. They get your little ducks in the row with these, these plates that are charged. And then step 4 is now we're just constantly monitoring until something goes wrong,
So that air is creating the bridge, basically, right?
I think so. The ionized particles.
That's
and it might
awesome,
be,
actually,
too, that some of the radiation itself, like those alpha particles, might be involved. But my imagination is, this is chemistry off the cuff. This is in my imagination, is that there's all kinds of ionized particles in there. Like
right.
Maybe there's some alpha particles that picked up an electron. Maybe there's some alpha particles that picked up 2 electrons, you know?
Yeah.
And then they probably stole it from someplace. So there might be like an oxygen that's lost an electron.
Yeah.
So in my mind, it's sort of, it's a whole mixture of different, types of ions going to complete the circuit.
Okay. Yeah.
Either way, electrons are flowing to make an electric current.
Yeah.
That tells the smoke detector that everything is okay.
Yes. And there's a plate that really wants those electrons. There are different charged things that are gonna, if they can find a way, if there's enough things available, they're gonna want to do it.
Yeah.
So that helps too. It's like if the conditions start happening, one of us is ready to take some electrons and one of us has some extras.
Right.
And
And I think going back to the battery episode where we talked about the current of electrons flowing through and how when there's no battery that interrupts it, and when the battery's present, it completes the circuit.
Right.
That is almost the exact same idea. Like I just kept thinking about batteries.
Yeah.
Only instead of batteries, the thing that's completing the circuit in this case is the ions that are created by the radiation, which is crazy.
Yeah. That is so crazy.
And there are probably also batteries on the other side of it too.
Yeah.
That are powering it. So there's like a battery bridge and an ion bridge that it's like circulating through.
Yeah.
So
dang, that's so crazy.
That was a good one. Okay, well, thanks. That was really fun. And speaking of fun things, do you have any questions on that before we go in?
I think I mostly get it. I mean, I think I'm close enough. But I guess also we'll build on, even though it'll be a different method, we'll be building on this idea next week with...
It'll be really different. There's no radiation in the other kind.
Well, it gives me a chance to, understand something that's completely different chemistry-wise, but has a similar function in the world, which is pretty cool.
And I'll probably have you compare and contrast the two as well next week.
You asked me if I had something fun for my week. Okay. Well, I think the biggest highlight is that we've been trying to find a time for my mom and my brother to come visit from Abilene. And unfortunately, my brother had some work stuff come up, so he couldn't come. So he's going to come a different weekend. My mom got to come hang out with us this past weekend.
Oh, nice.
And that was really fun. Obviously, my son just loves getting time with her and stuff. So that was really fun. A lot of cute moments and just also like a lot of just chilling and no huge events, nothing like crazy or whatever. We cooked dinner one of the nights, which was really fun. But yeah, it was just good to get some time together. And I think also this is kind of fun because my son being like 2.5, he gets excited about people coming to visit a lot more than he used to. And like we can kind of build it up across the week and stuff like that. And he just, I don't know. And he's like, he's very much like loves everyone being here all the time.
Yes, he really does.
Yeah.
He's always excited to see me.
Yes.
It's like, it does not matter.
Yep. And whenever people leave, even if they're just like dropping something by or whatever it is, or even if they're like, my mom was here for like a whole weekend, like multiple days, he just has this general, like, why did they even need to leave? Like, why did they go somewhere else?
I was over here one night to record, and then I left, and then Mason came to do coffee because our lives are so intertwined. And Mason told me, Josh's son, he kept talking about how sad he was that you left.
Yeah. He's like, where's Melissa? And stuff like that. Like, sometimes I'll just be like, come to my house. Like, they'll say something like that. Like, it's like, dude, people have their own places to live and their own things to do, But he doesn't get that. He's just like, why can't we all always be together?
One time Emily had to explain to him that I had to go clean.
Yeah.
And she told him that our house is a big mess because that's what she uses to describe cleaning up. And I was like, oh, great. So you're just telling him our house is a big mess.
Yeah.
But it was cute. It's cute to imagine him being.
And it's relatable to him because he knows, like, we'll be like, dude, we got to clean up. It's a big mess. You got a lot of toys out or whatever. So even though it does make it seem probably worse than it actually is, but he can be like, oh, big mess.
No, it was a big mess.
Oh, okay.
So it just is so cute how it's like you have to give him an explanation for what's happening.
Yeah. What about you? What's been going on in your week?
Mine's sort of similar in that it involves traveling, but not someone traveling to visit me. I left.
Yeah.
I went to Auburn.
And you're gone for a while.
I'm gone all the time now. I'm in this weird phase, and I kind of thought it would calm down in the new year, but maybe not. Maybe this is just the way this job is. I think part of it is by my own design because I really like to work in person with the people that I'm working with. So I go to Auburn once a semester for about a week to work with the grad students that I work with, virtually all the time. And it's really nice to get that FaceTime in, and it just makes it just a little bit more comfortable and easier to have that community. And so I really enjoyed it. And actually Mason came with me.
Oh, cool. Yeah.
For just like the first few days. So we got to kind of have a little weekend getaway, and he got to meet the people I work with too. Cause it's weird. You've never met these people I spend all my time with.
Right. And they know things about him, and you've probably told Mason things about your coworkers, but never have the two met. And it's not easy to accomplish that. It's not like, oh, we're going to dinner after work or something. It's like it takes extra effort to pull it off.
But it was really fun. We got to stay in this really cute Airbnb in Atlanta. And I just had a really good time. And I always really like working with my coworkers. But yes, and my traveling schedule is wild. So expect to keep hearing me talk about it. Because I've got a conference in March. And then April's pretty chill, but I'll probably go back to Auburn in May. And then another conference it might be in July. So maybe May, June, I'll probably go back to Auburn. Yeah.
Oh, yeah.
And then, so it'll probably go at a lower rate, but I just, it's kind of fun. I'm one of those people who travels for work now.
Nice.
Yeah. But it is weird because then I haven't seen my friends at home for a while, So then it's like when I'm trying to plan something, I was like, oh yeah. Maybe in 2 weeks. So.
That's cool though.
Yeah. So that was my fun. It was fun to go to Auburn and work with my coworkers. I really enjoyed it.
And also it's cool that Mason finally got to go because who knows how often that'll actually be able to happen. So.
And then after he went back home and I was working, I was able to say like, oh, I had dinner at this place and he's been there, And so that made it, nicer too.
Yeah, that's true.
So that was my happy thing for the week.
Very cool.
Yeah, thanks. Thanks for learning about smoke detectors and having something relatable about it. The fact that you don't have one in your kitchen, which is concerning.
Yep, very concerning.
And thanks to all of our listeners and viewers who make this show possible because we wouldn't be able to learn all about chemistry and share about it.
Yeah. And didn't this topic come from a listener?
Yes. And that was a really good idea. I had never thought about it. And then I was gripped with the fact that I didn't know.
Yeah, seriously.
So that was a really good one. Thanks. Shout out again to SD Pete on Instagram.
SD Pete. Well, we've got a lot of our own ideas about topics of chemistry everyday life, but we love hearing from you guys. And y'all's ideas are some of the best episodes we end up having. So please send those our way. If you've got an idea, you can reach out to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can go to patreon.com/chemforyourlife or tap the link in our show notes to join our super cool community of patrons. If you're not able to join, you can still help us by subscribing on our favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to share chemistry with even more people. And also you can subscribe. Dang it.
Yeah.
Why did I even...
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and this episode was made possible by our financial supporters over on Patreon. It means so much to us that you want to help chemistry be accessible to even more people. Those supporters are Avishai B., Bri M., Brian K., Chris and Claire S., Chelsea B., Derek L., Emerson W., Hunter R., Jacob T., Kristina G., Lynn S., Melissa P., Nichole C., Stephen B., Shadow, Suzanne S., Sam N., Stephen B., Timothy P., and Venus R. Thanks again for everything you do to make Chemistry for Your Life happen.
We'd also like to give a special thanks to our team of reviewers who reviewed this episode before it went out. And if you'd like to learn more about today's chemistry lesson, you can check out the references for this episode in our show notes or on our website.